Okay, hello class, and welcome to 4.7, Springs and Conservation of Energy. So this is the last topic for Chapter 4. It carries off of what we just saw in 4.6 with springs, and we're going to see how it relates to conservation of energy. So you might remember conservation of energy, we said that, that energy is neither created or destroyed, it just is converted between different forms. Well, that law applies, it applies to elastic potential energy as well. It applies to elastic potential too. So we can convert between, let's say, kinetic energy and elastic potential. We can convert between gravitational and elastic potential. And of course we can still do kinetic to gravitational and any sort of other energy conversion as well. But these are the ones we've seen so far. So we're going to look at a few problems that involve these three now, all trading places. So this first one says that a model car of mass 5 kilograms slides down a frictionless ramp into a spring with a spring constant of K equals 4.9 kilonewtons per meter. So part A says the spring experiences a maximum compression of 22 centimeters. We want to determine the height of the initial release point. And it might seem like we're not given a lot of information, but we're given everything we need. If you look at the picture to the right, we have our car starting at this high point. It's going to lose all of its gravitational energy, convert it to kinetic, so it's going to convert it to kinetic along here, and then it's going to hit the spring and it's going to convert all that kinetic into elastic. Okay, so we start with pure gravity, then we turn to pure kinetic, then we turn to pure elastic. So this is quite nice. We've got our spring, and we're told that the spring goes to a maximum of 22 centimeters. So we can use our equation E, our elastic energy, is equal to 1/2 K delta X squared. And we have K, which is 4.9 kilonewtons, so times 10 to the 3. Our delta X is 22 centimeters, so 0.22 meters, and we want to square that. And that gives us an elastic potential energy at the end here of, let me just see here, 1/2 times 4.9 times 10 to the 3 times 0.22 squared. This gives us 118.58 joules. Okay, so we have our initial energy. That's all the energy we have to work with. And we convert that in the end, or sorry, that's not our initial. That's our final energy, and that comes initially from our kinetic energy, our gravitational energy, sorry, at the start. So we can figure out our Eg is going to equal, well, mg delta y. Okay, and we want to find the initial height. So we want to find delta y is equal to Eg over mg. Now we know Eg at the beginning has all of the energy, so it's going to have that full 118.58 joules that we later convert into elastic. Okay, and I can divide by its mass here, which is 5 kilograms times 9.8, and this should give us, divided by 5 divided by 9.8, should give us 2.42 meters. And there we go. That's our initial height. Part B, we want to calculate the speed of the model car when the spring has been compressed 15 centimeters. So at this point here, we have some elastic potential and we have some kinetic energy. So we can say our total energy is equal to EE plus EK. Okay, and we also know that it's equal to, in total, 118.58 joules. Remember, that's the total amount of energy we have to work with. That's how much we started with. So let's see. Ek, our kinetic energy, is going to equal Et minus Ee, which is here our total energy again, minus elastic, which is 1/2 k delta x squared. So well, now we can maybe substitute in our 118.58 minus 1/2. Then we use our value of k. K was 4.9 times 10 to the 3. And our delta x is 0.15 meters, and we square that. So let's see, we get now a kinetic energy of 63.9 joules. And if we go over here, we can say Ek is equal to 1/2 mv squared. So v is going to equal the square root of 2 Ek over m. So the square root of 2 times 63.9 over our mass, which is 5 kilograms. And this gives me then a value of 5.1 meters per second. So I think it's pretty neat what you can do with energy once you know how much you have to work with. And our last piece here, determine the maximum acceleration of the car after it hits the spring. So when it hits the spring, the further it compresses the spring, the more force it gets back from it. So the maximum acceleration is going to be when the spring is fully compressed. Okay, so when the spring is fully compressed, that means that we're going to be at this maximum that they already told us, which was delta x is going to equal 0.22 meters. Okay, and we can get our force. Well, we know that the we want to get that our x force, Fx, is equal to negative k delta x. And so we can figure out what our x force has to be here. It's going to be negative. We've got, okay, sorry. I'm just going to make our delta x negative as well because it's to the left. Okay, so this comes out to negative 4.9 times 10 to the 3. And our delta x here is negative 0.22. So this gives us a force to the right of, one moment here, 4.9 times 10 to the 3 times 0.22 of 1078 newtons. Good. And we know that the net force here, that's equal to Fx, which is equal to ma. And so to solve for acceleration, a is equal to Fx over m, which is 1078 over 5, which gives us 2.2 times 10 to the 2 meters per second squared. There we go. Okay, that's that whole problem done. Let's take a look at the next page. The next one says a 48-kilogram child bounces on a pogo stick. At the lowest point of one bounce, the compressed spring in the stick has 120 joules of elastic potential energy as it compresses 0.19 meters. Assume that the pogo stick is light enough that we can ignore its mass. So part A, we want to determine the child's maximum height during the jump following the bounce. So this is where the child is going to fully convert that elastic potential energy into gravitational potential energy. And that's, I think, simple enough. We've got that we start out with 120 joules, and now we can say that that our Eg is equal to mg delta y. Good. And it's also equal to 120 joules. So if we want to solve for delta y, it's going to equal Eg over mg, which is 120 joules, over our mass, which was 48 kilograms, times g, which is 9.8, and this gives us a value of 0.26 meters. There we go. That's how high the child will jump. And part B, determine the child's maximum speed during the jump. Okay, maximum speed. So this is where we're going to convert. Well, I guess we need to figure out first where it's going to have the maximum speed. So if you think about this situation, the pogo stick is accelerating the person up or down. So as the child goes down on the pogo stick, it's slowing them down, and then it pushes them back up, and the point at which they're going to have the maximum speed is at the pogo stick's equilibrium point. Okay, and so that equilibrium point is 0.19 meters above that lowest point. We've been using the lowest point as our reference point. When we did our calculation here for gravitational potential energy, we were calling that lowest point 0. And then we were measuring above that. So we need to keep doing that. So that means that at this point, at the equilibrium point, we're going to have our total energy is going to be equal to some gravitational energy and some kinetic energy. And we're not giving any energy now to the pogo stick, to the elastic energy. That's why this is where we're going to have the most kinetic energy, because we're taking it all away from the spring. Good. Okay, so the gravitational energy here, it's going to be mg delta y plus 1/2 mv squared. Okay, and our total energy, we know the total that we have to work with is 120 joules. Good. Now our delta y in this case is going to be 0.19 meters above the ground. So if we want to solve for v, it's going to be equal to the square root of, and this is going to be a mouthful, I think, but we're going to say it's going to be 2 over m times 120 minus mg delta y. And if I plug in some numbers now, we're going to have 2 over, our mass is 48 kilograms, 2 over 48 times 120 minus 48 times 9.8 times our delta y, which is 0.19. Now, you could have done this in a slightly different order. You could have found first the kinetic energy and then just worked from there. I've maybe made it more complicated than it needs to be. But here we go. If you go ahead and do that equation, you should get a speed of 1.1 meter per second. Excellent. Okay, we have one more problem here, and then at the very end we're going to talk about another concept but not actually do any math with it. So this next problem here, a block with a mass of 2 kilograms is held against a spring with a spring constant of 250 newtons per meter. You can see the picture to the right. The block compresses the spring 22 centimeters from its equilibrium. After the block is released, it travels along a frictionless surface and then up a frictionless ramp. The ramp's angle of inclination is 30 degrees. First off, we want to determine the elastic potential energy stored in the spring before the mass is released. Okay, well, we know that E is equal to 1/2 k delta x squared. And let's see, that's going to be 1/2. We have our k value, 250 newtons per meter. Delta x is 0.22 and we'll square that guy. This gives us a value of 6.05 joules. And we have our elastic potential energy. Now we want to calculate the speed of the block as it travels along the horizontal surface. Well, at this point we will have converted all of our elastic potential energy into kinetic. So now kinetic is equal to 6.05 joules, which is equal to 1/2 mv squared. And we can solve this for v. V equals the square root of 2ek over m. That might start to look familiar now. We've used it a few times. So the square root of 2 times 6.05 over the mass. Our mass was, let me just check here, 2 kilograms. So we get the square root of 6.05, which is equal to 2.46 meters per second. And we're not quite done with this problem. There's a part C on the next page. Part C. Determine how far along the ramp the block will travel before it stops. Okay, so we want to find our distance, the hypotenuse along the ramp. So I'll just redraw this part of the problem here. We're going to have some delta y, and we've got some angle 30 degrees here, and this is going to be our d. We want to solve for d. Okay, well first off, we're converting all of our energy into gravitational energy. So Eg is equal to mg delta y, and that's going to be our full 6.05 joules. It's going to get all of that. Great, so we can find delta y. Delta y is equal to Eg over mg, which is equal to 6.05 divided by our mass, which is 2 times 9.8. And this gives us a delta y value of 0.308 meters. Good. Now, it's just a matter of trigonometry to find d. We can say that sine 30 degrees is equal to delta y over d, the opposite over the hypotenuse. And we can rearrange that then for d. So we get d is equal to delta y over sine 30 degrees. So we'll use this over here. D is equal to delta y over sine 30 degrees, which is equal to 0.308 over sine 30. And that gives us a value of 0.62 meters. And that's how far along the ramp we go. Now I think these are all problems that would seem like a mess if we didn't know about energy. If we were just trying to do this all with kinematics equations, oh boy, I think this would be really tricky. And so I think energy is super cool. It makes all of these calculations a lot cleaner. Good. All right, last topic here, damped harmonic motion. Now, mostly we're just going to talk about this concept. First off, perpetual motion machine. You may have heard of the idea. The idea is it's a machine. Sorry, 1 second here. It is a machine that can operate forever without restarting or refueling. Without restarting or refueling. And so you can think like a pendulum. If you know grandfather clocks, they keep on ticking back and forth, but every now and then you need to wind them. There is no such thing as a perpetual motion machine. It would have to be the case that there's no energy loss, and we always have some amount of energy loss due to friction, things just rubbing against each other. So in reality, no such thing as perpetual motion. Instead what we have is damped harmonic motion. And this is periodic motion affected by friction. So this is what we have instead of perpetual motion. It eventually goes down to zero. So you can see the picture to the right here. We have some oscillating patterns that go closer and closer to zero and eventually just stop moving. So we have three types of damping. This is underdamped, and you can see on the picture they're labeled. So underdamped is the number 3 here. You can see it goes up and down. This is where the oscillation slowly reduces with time. Okay, and overdamped is where the mass slowly returns to zero. Or slowly returns to equilibrium, I'll say. Equilibrium being this 0 point without passing through zero. Okay, and you can think of, you know how some doors, when you try to close them, they close very, very slowly and eventually just reach the closed point. That's an overdamped system. And you can see that's line number 1 to the right. And then halfway between those, somewhere in the middle, is this critically damped, where the mass returns to equilibrium as quickly as possible, without passing zero. And so in the picture to the right there, that's line number 2. And just to give you an idea of where that could be useful, one example is shock absorbers. Those are critically damped. So shock absorbers on a car are critically damped. And that's because we want them to reduce any shocks on the road to zero and bring you back to equilibrium as quickly and as smoothly as you can. But one problem is that as they wear out, they become underdamped. Which is where they rock back and forth again. So making the car bounce up and down. And you might have experienced that in an old car. When you hit a bump, it really keeps on bouncing up and down. So that's where it has become underdamped. Okay, that's the end of the lesson. It's the end of the chapter. I hope you enjoyed it. Have a great weekend, and we'll see you on Monday. Thanks.